Hi everyone, welcome to the 7th video. This is actually going to be our last video on factoring. We're nearing the end on polynomials. And I'm just titling this video More Factoring Tricks because that's pretty much what you can expect here. So we're going to go through 2 factoring tricks for just the pre-calculus group, and then there's going to be one more for pre-calculus 10. So pre-calculus 10 is just going to be a slightly longer video. But let's get started. Okay, so the first factoring trick, these are all factoring tricks that you use when you have something that's higher degree than a quadratic. So remember, with our 3 quadratic tricks, we can completely factor any quadratic. These are just some extra tricks for dealing with those higher degree things. So the first trick is the simplest. This is a trick that says that if you don't have a constant term, for example, in this polynomial that I have here, 2x to the 4th plus 3x cubed minus 5x squared. So there's no constant term there, and that means that I can factor out some x's. And whenever you see that, then it is always a good idea to just go ahead and factor out those x's. That's what I've done here. So I've taken, because x squared is the smallest degree of x, I've just gone ahead and taken that out because it's showing up in all of the terms. So I am using some basic exponent rules here to say that what's left is 2x squared plus 3x minus 5. Now, what's left is, in this case, a quadratic. So I could keep factoring this by using the quadratic formula, but I'm not going to go ahead and show that to you again. This is not done factoring this polynomial, but if you just go ahead and find the roots of this, probably using the quadratic formula, then you could write this this last part as 2, leading coefficient, times x minus the first root times x minus the second root. Now, what would the roots be altogether? Well, they would be the roots from this quadratic together with 0. Because remember, if you're factoring out this x, it might not look like a root, but that x is always equal to x minus 0. So just as I say here in the bottom, whenever you can factor out x's, that means that 0 is one of the roots. And in this particular example, because it's showing up twice, it's actually a root of multiplicity 2. Okay, so that's the simplest trick. So this next trick is a little bit more complicated, but I call it the substitution trick. You might know it by some other names. So I'm going to use this example to illustrate what that is, and I'm going to go ahead and write this example out. So, okay, I want to factor this over the real numbers, and what I notice about this to start with is that it has x to the 4th and x squared. That means that all the powers of x that I see are multiples of 2. So in this case, what that will let me do is it will let me substitute in a new variable for x to the 2. Okay, so I'm going to write that here. That new variable I'm going to call a. You can call it whatever you like. So what that will let us do, I'm going to write this again. We can write this first term as x squared squared. The second term can stay x squared, and the last term is the same. Now I can replace every x squared I see with a. So this becomes a squared plus a minus 6. And now I'm going to go ahead and factor this because I've turned it into a quadratic. So now I can factor it using all the other quadratic tricks I know. In this particular case, it factors pretty easily by hand. And it will factor into a plus 3 times a minus 2. Okay, now I'm not done because I need to substitute that a back for x squared. Okay. And now if I do that, I see that I've turned it into quadratic times quadratic. So again, because what's left are just quadratics, I could use any of my quadratic tricks to factor those. In this particular case, it's not too hard to see that the x squared plus 3 part doesn't have any roots, because if I set it equal to 0, then I'm going to be taking the square root of -3. So it will factor over the complex numbers, but not over the real numbers. And I'm asking for a factorization over the real numbers. The x squared minus 2, however, will factor. And you can use any of those tricks, but in particular, it's a difference of squares. So I'll show you how to rewrite that x squared minus 2. Running into the edge here, so I'm going to write this down here. Okay, so in the end, what we have are 3 factors. We have this x squared plus 3, which doesn't factor anymore over the real numbers, and then x minus square root of 2 times x plus square root of 2. That should actually be one product. I just wasn't quite able to fit it in. So I end up with 2 real roots, square root of 2 and minus square root of 2, and then this quadratic which doesn't have any real roots, x squared plus 3. Okay. Now, the important thing to keep in mind when you're doing this substitution is to be able to write something like this. Like I wrote x to the 4th as x squared squared. And the important rule to remember, the important exponent rule, is that if I have x to the a to the bth power, that's the same thing as x to the a times b. So this is sort of how you split up exponents under products. You write them as nested exponents, and that's the key to making this substitution trick work. So in this particular case, it's because everything was a multiple of 2. But in other cases, I could have everything be a multiple of 3, and then I could substitute a equals x cubed. That would be a little trickier, but I could definitely do that. Okay, so this is it for the pre-calculus part, but I'm going to keep going for one more bit for the pre-calc 10. Okay, so the last thing we're going to talk about is the rational roots theorem. So when do you use the rational roots theorem? So you use this when you need to come up with a guess for a root. Remember that in previous problems, I've either given you the root to a cubic, or I've let you use your calculator to guess what a root is, right? You use your calculator, graph it, and then see what that x-intercept is. But if you don't have either of those tools, if I didn't tell it to you and you don't have your calculator, then it's really hard to come up with a guess for a root. And the rational roots theorem gives you one tool that you can use to make guesses, because it tells you what the possible rational roots could look like. Okay, so the way this theorem works is that if we have a polynomial, f of x, and that polynomial has a rational root, let's say p over q. So that's a fraction. That means p and q are whole numbers. And I'm going to go ahead and say that that fraction is reduced. So I've kind of gotten rid of the common factors. I've divided out the common factors if I need to. Okay, now what the theorem is actually saying is that in this case, the numerator, the p, has to be a factor of the constant term of the polynomial. And the denominator q has to be a factor of the leading coefficient. Okay. And as I was saying earlier, what this lets you do is it lets you create a list of possible roots. They don't have to be roots, but if there is a rational root, it has to be in that list. So there's at least a decent chance that out of all of these possible roots that you get from the theorem, at least one of them will actually be a root. So this is easiest to see in an example. So I'm going to go ahead and show you an example. So in this case, I'm asking, what are the possible rational roots of this cubic polynomial? And I'm not going to go ahead and see if any of them are, but I could use something like synthetic division to test if any of these are actually roots. But let's just go get the experience of using the theorem first. Okay. So the first thing is to point out the leading coefficient and the constant term. The leading coefficient is this 2. So that's the leading coefficient. Remember my first video on polynomials where I talk about that. And then this is the constant term. And it does include the minus, although it doesn't actually affect the theorem whether there's a minus there or not. Okay, so what the theorem said is that P has to be a factor of 2. And Q is a factor of, oops, I got it backwards, but this is one of the common mistakes, so it's probably good that you see me do it. Let's erase that. Okay. Yep, what did I say in the theorem? I said that P has to be a factor of the constant term. So it has to be a factor of -3. Q is a factor of the leading coefficient, which is 2. So what are the possible, let's talk about possible P's and Q's. So what are the factors of -3? And they could be positive or negative. Well, 3 is a prime number, so the only factors are 1 and 3. And just keep in mind that everything has a plus or minus. So the possible P's are plus or minus 1, plus or minus 3. Possible Q's are, again, so Q is a factor of 2. So what are the factors of 2? 1 and 2. When I include the plus or minus, that's plus or minus 1, plus or minus 2. Okay, so that means that the P over Q's, so there's a lot of possible combinations because I've got 4 P's and 4 Q's, but you don't quite get that many P over Q's because you get certain things like minus over minus, which is the same as plus over plus. So I'm only going to write down the final list after you realize that some of these are actually the same. So from 1 over 1, I can get 1 minus 1. So from 3 over 1, I can get 3 minus 3. So from the P equals 1, Q equals 2, I can get 1/2 and minus 1/2. And then from P equals 3, Q equals 2, I get 3/2 minus 3 over half. So a lot of people will just like to write these as like plus or minus 1, plus or minus 3, etc. So the list doesn't quite get so long. But that's 8 possible things to check. That's already a lot, right? So in this particular example, it would be a lot for me to ask you to check which of those are actual roots. But, you know, if I had a polynomial like this and there was no other trick in my book and I didn't have my calculator, this is what I would start doing. I would start testing 1, minus 1, 3, minus 3. And I looked this up. In this particular case, the only rational root is x equals 1/2. So I would go through that list, and then by the time I got to 1/2, from the synthetic division, I would get a remainder of 0, and that would tell me, aha, I finally found a root, and I even know what the quotient is when I divide by that root, because it's sitting right there in the synthetic division. So we'll do some more examples of this in class, but I think for right now, if you can actually get that list of roots coming from the theorem, then you're successful. Okay, so I'm going to stop things there. See you guys in class. Hope you have a great day.